Yet. Oh, we only see.
No, I just shared my screen. Sure. Can you see my screen now?
And you have 10 minutes.
So it's actually full screen. I don't know if it's so this is a full screen. I'm not sure if it's clear enough, but
You can proceed.
okay. Okay. Hello everyone. So my name is James Onyejizu, and I will be presenting our work on modeling the impact of passive ventilation systems on multi-zone thermodynamics. So to motivate this work, we start by mentioning that in general, buildings contribute to about 40% of the energy used in the US, and in particular, HVAC systems accounts for 36% of the energy used in the US commercial buildings. And of course, 30% of this, energy used by heating, ventilation, and air conditioning systems is wasted due to system inefficiencies, and this can result to great financial losses. And these systems rely on fossil fuels, which produces tons of CO2 that can possibly lead to environmental degradation. Now, one question comes in mind. So, what could be an alternative to such systems that rely on fossil fuels? Now, one system we could use in this regard would be to adopt passive ventilation systems, which leverage external airflow without over reliance on electromechanical systems. Now, if adopted properly with appropriate control strategies, such systems, passive ventilation systems in this case, can complement traditional HVAC systems and therefore provide significant energy savings through passive climatic resources for heating and cooling. Now, multi-zone buildings, on the other hand, presents a complex challenge for energy efficiency due to the distinct thermal zones as well as the complex thermal interactions between the different zones. And based on this, a need exists to study the impact of passive ventilation systems on multi-zone thermodynamics. Now, we summarize the key contributions of this work as follows. First, we develop a novel locally interactive bilinear flow model for passive ventilation systems. Next, we propose a novel two-step parameter estimation method for such systems. And finally, we study the impact of such systems on multi-zone thermodynamics. Now, the locally interactive bilinear flow model adopted in this study assumes a graph-based structure where the state of the zone represents a node, and the relationship or the thermal interaction between adjacent zones and the ambient represents an edge. Now, heat flow coefficients, known as the thermal conductances, parameterizes heat flow between adjacent zones as well as it flows between a particular zone and the ambient. Now, given a set of zones adjacent to zone I, then the thermodynamics of zone I is a function of the rate of heat change, which is basically a function of the thermal interaction between zone I and J, the thermal interaction between zone I and the ambient, as well as active heating or cooling sources. Now, the term BI parameterizes the active heating or cooling source, and this term is a function of the vent openings. Also, big theta in this equation represents the vector of all passive elements, doors, and windows, in this case, which are controllable. Now, we note here that based on the ILIBF model, we impose an assumption of local dependence of the system states, in this case, the temperature, on the passive elements of the multi-zone building. We say that the passive element in each zone directly impacts the temperature of that zone. Now, while this locally interactive nature of the ILIBF model might seem natural, this might not hold in certain scenarios. Now, in this work, we focus on assessing the impact of the window and door openings on the thermal dynamics of the multi-zone buildings. And therefore, the ILIBF model greatly reduces to this, where theta in this case represents the door opening factor with respect to adjacent zones, as well as the window opening factor with respect to the thermal interaction between the ambient and a specific zone. Now, since the vent openings in our studies are constant, the term BI does not account for the dynamic changes in the vent openings. And Q here represents the internal heat gain. Now, the parameters from these models are estimated through measurements. Next, we introduce the novel two-step parameter estimation process, which involves applying the discretized reduced model on measurements using non-negative least squares. And then we develop a polynomial fit method, which basically is used to study the impact of different combinations of door and window openings on the thermodynamics of the building. For evaluation results, we considered an energy plus model of a small office commercial building provided by the DOE. Now, this model includes 4 doors and 2 windows, and the HVAC system consists of a centralized three-zone configuration with a single loop. Now, to evaluate the reliability of our proposed approach, we leverage the root mean square error values and plot the visual comparison of both the observed temperatures with the model predictions. Now, based on the RMSC values, we conclude that indeed our locally interactive bilinear flow model can capture the zonal thermodynamics of multi-zone buildings. In addition to this, we also study the effect of door and window opening factors on the thermodynamics of the multi-zone buildings. Specifically, we keep the window opening factor fixed at 5% and open the door between zones 2 and 3 from a fully closed state to a fully open state. Now we observe that as we open the door between zones 2 and 3, the thermal conductance between these zones increases, which implies interzone coupling. We also note that the thermal capacitance of the three zones remains constant, which is kind of expected, since the thermal conductance would only, the thermal capacitance would only depend on physical characteristics such as volume and mass of the zones. Now, based on this study, we conclude that indeed the ILIBF model can capture the impact of passive control elements such as windows and doors. The next approach involves evaluating the reliability of the two-step parameter identification method. Now, the second step, as mentioned earlier, could be seen as a reduced complexity approach, where the goal is to, identify the parameters for different combinations of window and door opening factors. Now, for this, we estimate the thermal conductance across the window opening factors at 2.5% increments for a fixed door opening factor. Next, we also estimate the thermal conductance across the door opening factor at 25% increments for a fixed window opening factor. And then, based on this, we fit an estimate using a constrained second order polynomial. To evaluate our results, we show the RMSE values for different door and window opening factors. Now, we compared the RMSE value based on the model identification and the RMSE value based on the polynomial fit. Now, based on this, or based on the values, we say that the model indeed achieves good accuracy even on untrained combinations of window and door opening factor. And further, this is particularly important because the parameter estimation process enables model evaluation for. Okay.
Can you wrap it up?
Yeah. So in summary, this can be useful for fitting models to many passive elements where data collection for each combination is time intensive. And in conclusion, based on our study, we have proposed and evaluated a locally interactive bilinear flow model. Next, we proposed a two-step parameter estimation method for passive ventilation systems. And lastly, we validated our approach on a DOE Energy Plus prototype building, showing accuracy with fewer parameters. Thank you.
One quick question while Yang set up. But if question for James, but keeping it very quick. Not then industrial going to be on causal analysis to understand over buildings.